Hello everyone! Today I'm presenting our work called Polarity-Aware Probing for Quantifying Latent Alignment in Language Models. Large language models may produce safe aligned outputs while internally encoding harmful or contradictional beliefs. To study this gap, we introduce PA-CCS, an extension of contrast-consistent search. PA-CCS evaluates alignment without relying on model outputs by probing hidden representations, allowing us to detect misalignment that would otherwise remain hidden. So, language models often appear safe to filtering, moderation, or alignment training, but surface behavior does not necessarily reflect internal representations. This is evidence that models can encode harmful or contradictory beliefs in hidden states, even if they never output them. So, this discrepancy between surface behavior and internal structure motivates that we need probing methods that operate inside the model rather than on generated text alone. So, our method is based on CCS, and contrast-consistent search, or CCS, is an unsupervised probing method designed to extract latent beliefs. This method is really simple. We have a statement, and we append to the statement yes and no, pass this through the model, and trains a linear probe to identify a belief direction in activation space based on difference in hidden representations. But CCS evaluates methods and evaluates each statement in isolation, and it does not test whether internal representations remain consistent under polarity change, such as negation or safe harmful flips. As a result, CCS cannot attest whether harmful and safe content is encoded coherently. So this limitation motivates by PA-CCS. So PA-CCS extends CCS by making polarity explicit. We define a pair of statements, one safe and one harmful, representing opposite sides of a polarity axis. We attach both yes and no to each statement, this is penalty, and analyze all outputs of the model. We extract hidden representations for all four forms across all layers and apply CCS layer-wise to this polarity-aware set. This allows us to test whether internal representations behavior are coherently under polarity transformations. To evaluate this setup, we introduce three datasets. First dataset is the mixed dataset, and this dataset includes paraphrased and negated safe harmful pairs. Second dataset is not dataset, and this dataset consists only of strict negations. And last dataset, but not least, is TTT dataset. And this dataset is identical to no dataset, except the negation token is replaced with a meaningless token. If the probe really captures semantic polarity, the performance should degrade on the TTT dataset, and this is really exactly what we observe. The second step of our method is the metrics. PA-CCS use three metrics to evaluate internal alignment. The first metric is Empirical Separation Accuracy, and this metric measures whether harmful and safe representations form distinct clusters. Second metric is Polar Consistency. This metric measures whether belief directions behave coherently under polarity flips. And last metric is Contradiction Index, and this metric measures whether the model agrees with both a statement and its negation. Together, these metrics characterize polarity-dependent internal alignment behavior. So, and now about results. Mixed and not datasets produce very similar metric profiles, and this indicates robustness to phrasing variation. In contrast, replacing negation with a meaningless TTT token significantly degrades polar consistency and increases contradictions. So this demonstrates that PA-CCS captures semantic polarity rather than superficial word patterns. So the second result is about model size. As model size increases, more layer exhibits high separation accuracy and higher clustering and PA-CCS space. So high-performing layers tend to cluster near a polar consistency of approximately 0.055 and contradiction index of approximately 0.31. This indicates that larger models develop more structured and consistent internal polarity representations. The next result is about architecture comparison. So, encoder models show lower variance but weaker separation. Decoder-only models show stronger separation but greater variability across layers. Encoder-decoder models exhibit the highest inconsistency. And this indicates that polarity-aware alignment behavior depends strongly on architectural design of the model. The next one result is about instruction tuning. So instruction-tuned models consistently show higher separation accuracy, lower contradiction, and more stable polar consistency across layers. And this suggests that alignment training reorganized the internal latent space of the model, and alignment training recognized not just only outputs. And this is really interesting fact of from our experiment. And this is PA-CCS landscape. Each point in this plot in this space corresponds to one configuration of our CCS probabilities. The x-axis represents polar consistency and e-axis represents a contradiction index. Green regions correspond to alignment layers that clearly separate harmful and safe content, typically near PC 0.055 and CE 0.31. So blue and gray regions indicate little or no polarity signal. Red regions again indicate inverted or contradictionally internal beliefs. And this space, this is just all possible theoretical space of PA-CCS landscape. And this space is just important to understand metrics. So, PA-CCS offers a new way to probe internal alignment in language models. It reveals subtle, harmful, and safe signals encoded in hidden representations that output-biased affiliates often miss. It distinguishes consistent, inverted, and non-polarized internal states. And the method scales across model sizes and architectures and show that instruction tuning improves internal coherence and reduces contradictions. Overall, understanding alignment requires examining what model internally represent, not only what they say. Thank you for your attention, and if you have any questions, just contact somewhere of authors, and we were happy to answer on your questions.